All right, notice example 3. If a ball is thrown up in the air with an initial velocity of 20 meters per second off a cliff that's 200 meters off the ground, its height in y in meters after t seconds is given by y equals negative 4.9 t squared plus 20t plus 200. So y is the height, which is a unit of distance. T is time, which is seconds, unit of time. So we're going to have the horizontal axis, if we were to graph this, is t, and the vertical axis is y. And the vertical axis is representing a change in a distance, a height of this ball, and the horizontal axis is representing how much time has passed since the ball has been released. This is an equation based on the gravity of Earth. The acceleration due to gravity on Earth is negative 9.8 meters per second squared. That's exactly half of the gravitational pull of Earth. Okay, this is how fast it was going when it started. Okay, it was thrown upward 20 meters per second. That's a positive 20 meters per second velocity, and this is the initial starting point. So we're going to learn how to construct equations like that in a few chapters. All right, but they're not hard to make. But you need to know how fast it's going to begin with, where you started to begin with, and what planet you're on. Different planets have different acceleration due to gravity. So we typically are on Earth. Okay, the book didn't venture us off into Jupiter or something like that. I don't know if it can be on Jupiter, it's a gas planet, but maybe Mars. How about Mars? It probably has a different gravity. So anyway, you should say average velocity. All right, average velocity is a secant line. Okay, so the last two sections we've been doing secant lines, right? So the first section we have an equation, and we had our point of tangency, and we had our value of x away from that point of tangency, right? We found the slope of that, all right? And then as each secant got closer and closer and closer to that point, they became closer and closer and closer to the slope of the tangent line, okay? So what they're asking us to do is they want us to start at 5 seconds and go 0.5 seconds past it. Okay, this is one way of asking the question. So what they're asking me is they want t equals 5 and t equals 5.5. If you start at 5 seconds and last half a second, now you're 5.5 seconds. So the initial time, the starting point is 5 comma whatever, and the final time is 5.5 comma whatever. We have an equation here that represents what t represents based on these values. I'll open this up real quick and we'll see if we can get some numbers in here.
I think there's one like this on our assignment.
Yeah, the way they ask them is a little different, so I wanted to introduce you to this idea. Okay, mathematically trained eye can see, oh, that's what they're asking, but you know, you guys need to be trained a little bit, so I'm showing you different ways they can ask you the same question. So if we type in our equation, which was negative 4.9, I'm going to go x squared because my calculator doesn't understand t. Negative 4.9x squared plus 20x plus 200. And I'm just going to go straight to my table. Okay. Each one of these numbers, we're starting at 5 and going to here, 5 to here, 5 to here, 5 to here. So 5 to 5.5, 5 to 5.1, 5 to 5.05, 5 to 5.01. Same deal we did on the last problem, except we're going to zoom in on that way. Now, I could, if I wanted to, make an x comma m chart. Okay? I can make a slope formula for this. All this stuff minus whatever it is when y when 5 and then over x t minus 5. I mean, I can make a slope formula. What I'm going to do though is I'm just going to figure out the height of the ball. Okay, ball's thrown up in the air. Let's just figure out where it's at. All right, and then we'll see how to make the slope using a table of values, as opposed to finding the slope just by making a slope formula. All right, so make a distinction between the two techniques. What we did on Friday, we made a slope formula, right? Square root of x minus 2 over x minus 4, or x squared minus 4 over x minus 2, something like that. All right. Well, here, I'm just going to figure out what y equals for each of these. So I've got 5, 5.5, 5.1, 5.05, and 5.01. All right. That chart is an XY chart, and specifically it's a TY chart because that's what we're using. So if I make a chart here, time in seconds, that's an S. And height in meters. All right. When time is 5 seconds, its height is 177.5 meters. When time is 5.5 seconds, it's 161.78 meters. When time is 5.1 seconds, its height is 174.55 meters. When time is 5.05 seconds, its height is 176.04 meters. And when its height is time is 5.01 seconds, its height is 177.21 meters. The main mistake people make at this level is, just on Friday we made an X, M chart, and what was in the M chart was the slope, and the slope was what we were looking for, and we were ready to go, and we could see what it was zeroing in on, and we got the answer. Here I've made a TY chart, or an XY chart if you wish, all right? I've got my times, I've got my heights, I don't have any slopes. Slope is change in Y over change in X. Okay, I need to find changes here. So, when we talk about average velocity, how far did you go and how long did it take? That's what average velocity is. So to do part A, 1, 2, 3, and 4, if I want to find out the average velocity from 5 seconds to 5.5 seconds, I just look at those two spots on the chart. How far did I go? How long did it take? That's all it's asking me. All right, so it's just the slope of these 2 points. Y minus Y over X minus X. So 177.5 minus 161.78 divided by 0.5. Oh, sorry. Negative 0.5. I did this one minus this one, so I have to do this one minus this one. 5 minus 5.5 is negative 0.5. Feel free to write 5 minus 5.5 on the bottom. Okay, I think we can handle subtracting in our head. So, go to my calculator, type in parentheses 177.5 minus 161.78. Divided by negative 0.5. Comes out to negative 31.44 meters per second. All right? Does everybody see where that came from? Okay, again, it's just a matter of using the equation they gave me, this one, to find out where the ball is at every time they specified. And again, they didn't specify 5.5, 5.1. Again, starting here and lasting this much. So I've established what this meant in relation to real numbers that I was going to use for times. All right? How far did it go? How long did it take? Look at the next one. How far did it go? How long did it take? So we're going to do 177.5 minus 174.55. Divided by 5 minus 5.1, which is negative 0.1. So, again, parentheses. 177.5 minus 174.55 in parentheses, divided by negative 0.1, negative 29.5 meters per second. Oh, sorry, this one here was negative, wasn't it? Negative 29.5 meters per second. Next one. How far did it go? How long did it take? So part 3, 176 or 177.5 minus 176.04 over 5 minus 5.05, so negative 0.05. Parentheses, 177.5 minus 176.04 divided by negative 0.05 equals negative 29.2 meters per second. All right, finally the last one, from how far did it go, how long did it take? So the last one's 177.5 minus 177.21 over negative 0.01. Notice how I get the parentheses that time? I noticed that rather than going back to put the parentheses in, I just hit equals and then divided by negative 0.01. Just make sure you get the entire top evaluated first. So negative 29 meters per second. All right, so each of those is average velocities. Which one's closest to the actual velocity of the ball at 5 seconds?
29.
Very last one, right? Because 5.01 is closer than 5.5, right? So basically, if you imagine a ball falling, as it's falling, it speeds up, right? So its speed over this half a second should be more negatively than the speed after this 1/10 of a second, or this 5/100th of a second, or this 1/100th of a second. Okay? It's going however fast it's going at 5 seconds. As it continues to fall, it's going to be speeding up in a negative direction. So its speed increases. Too much, too much, too much, getting closer. All right, they're all too much because they're all not exactly that, but they're all getting a little closer. If I was going to take a guess at the instantaneous velocity, I'd probably just go negative 29 meters per second. It's not exactly that, but it's pretty close. 28.7. You think it's 28.7?
Yeah.
I think you chopped off a little too much. I think it's 20, well, let's see. Actually, it is negative 29. That's kind of crazy there. Actually. I think negative 29 is the right answer. But oh, so basically, all they're asking you to do for part B is to find instantaneous velocity. If you find a bunch of average velocities, and you see the average velocities are approaching some number, all part B is as a guess. Looking at these average velocities, they look like they're getting close to this number. So I'm going to guess that the instantaneous velocity is negative 29 meters per second. That's how you do part B. Anytime they ask you for instantaneous velocity, if you've already gone through all the trouble of finding a bunch of average velocities, what are they getting close to? Make a guess. I'm not going to say your guess is bad unless it's bad. Well, all this says is I'm probably going about 135 miles an hour, or meters per second. Yeah, probably not. Okay, they're approaching something, and then you make a guess depending on this. If you see this and you say negative 5, that's not a good guess. But
what about negative 20?
Negative 20, again, if you take a look, it only changed 2.44 over the span of these times. So it's going to be really close to this last number. So when you make these guesses, guess close to that number, that's a good guess. Bad guesses will be, I mean, obviously negative 30 would be a bad guess because it's not going to start speeding up again. All right? So it's obviously this or a little bit tinier than that. I usually go to the nearest whole number.
So negative 28.9?
I would not argue with that guess. All right, negative 28.9 would be a fine guess. But I usually go to the nearest whole number integer, unless it's like getting close to a 0.5 or a 0.25. I try to pick numbers that are pretty friendly. Okay. We get bigger and better calculus and better techniques, we can find the exact answer. There is an exact answer. All right, we can't find exact answers this way without just guessing it by accident. All right. Or not even by accident, but just kind of making a really good educated guess. Yeah. And in fact, there is a nice pretty answer like negative 29. All right. So anyway,
luckily.
Part C, find the average velocity over the given time intervals. Okay, so that's the whole problem. We're done. The end. All right. They may have asked us for the slope of the tangent line, but typically when they're talking about something about this, what they want is the speed. So the slope is what you're finding, the slope is the speed, that's it. This is the same exact type of question. Different starting time, but it's just a different way they can ask you. Okay, so basically we just finished the problem. We figured out at 5 seconds the speed of the ball is about negative 29 meters per second, which means it's going downward at 5 seconds and at a speed of 29 meters per second. At this one, notice 2 to 2.5, 2 to 2.1, 2 to 2.01, 2 to 2.001. Okay, this is just a different way of asking time intervals. Where the last one would have said starting at 2 seconds and lasting half a second. Starting at 2 seconds lasting 1/10 of a second. Starting at 2 seconds lasting 100th of a second. Starting at 2 seconds lasting 1,000th of a second. Now it's saying from 2 to 2.5, from 2 to 2.1, from 2 to 2.01. Basically, again, they're just feeding you the information they want for the t part. They want you to figure out the y part, and then you find out the slope of each thing. So again, how are they going to ask you to create a chart? That's what's going to change in the problems today. These are the two types of things they're going to do for you. So, if we take a look at the ty chart on this one, t is still in seconds and y is still in meters. And the t's we're going to use are 2, 2.5, 2.1, 2.01, and 2.001. How do I find y?
Calculator.
Calculator, go back, and we have the exact same equation, right? So I go back, and my equation's as it should be. Go to my table, clear out all the numbers here because they don't matter to me anymore. Delete, 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 delete. And we put it on our new numbers. 2, 2.5, 2.1, 2.01, 2.001. Now, I want you to notice here that it's 220.4. That actually goes out a little further. I think the reason we got the right answer on the last one is because I forgot about the whole rounding thing. So it probably was negative 29 point something, but anyway, I rounded because I took the rounded value. I forgot to look in there. One thing I'm going to say on quizzes when we get to these problems, do not round decimals in your chart. All right, so rounding is a bad thing. So the calculator automatically rounds because it only fits so much stuff in there. If you want to see the entire number, see that? And real quick, if I do 5.01 just for checking, 177.20951. It wasn't exactly 177.21. So that's why we got the exact right answer by accident. Okay, it doesn't always exactly hit the exact right answer when you round. So that's the point. What ends up happening is what Tyler was suggesting is like it starts going back up all of a sudden. Okay, that wouldn't happen usually. So if you see it start going back up, you probably round it. So I'm going to go over here to the y column and just make sure nothing's rounded. So 220.4. And the next one is 219.375. And the next one is 220.391. And the next one is 220.40351. And the last one is 220.4003951.
And you want us to write all of it?
Yeah, exactly.
Okay.
The whole thing. Don't round numbers in this chart. All right? So, what we've done is we compiled information about all 5 of the numbers in this. And notice there's 8 numbers, but 2 keeps happening. 2 to 2.5, 2 to 2.1, and so on. So whenever they do this, where the same number keeps happening again and again, and they keep going to different numbers, they're going to ask you about the instantaneous velocity at 2. So just like before, we had the point of tangency P staying where it was and everything getting closer to it. So we're sticking it 2 every time and we're getting closer to it. 0.5 away, 0.1 away, 0.01, 0.01. Keep getting closer to 2. So each one of those average velocities is going to get closer and closer to the right answer, so we can make a good guess for part D about the instantaneous velocity. So for part 1, how far did we go? How long did it take? So 220.4 minus 219.375 over 2 minus 2.5, that's negative 0.5. Use my handheld calculator for this one. I got negative 2.05. Is that what you guys got?
Yeah.
Meters per second. All right, 2. All right. How far did it go? How long did it take? All right, so we're going to do 220.4 minus 220.391 over 2 minus 2.1 is negative 0.1. And I got negative 0.09. All right, number 3. How far did it go? How long did it take? So 220.4 minus 220.40351 divided by negative 0.01, and I get 0.351.
Is it negative?
It's positive this time. All right, finally, the last one, number 4. How far did it go? How long did it take? So number 4, 220.4 minus 220.4003951 divided by 2 minus 2.001, so negative 0.001. Comes out to 0.3951, positive 0.3951 meters per second. All right. So we're supposed to be making this educated guess, looking at these numbers, what's getting close to. All right. Now it started off negative, smaller negative, almost 0. Then it switched to positive. Why did that happen? What do you think happened between 2 seconds and 2.5 seconds? We threw a ball in the air. The average velocity from 2 to 2.01 is positive. The average velocity from 2 to 2.05 is negative. What happened between 2 and 2.5? What? It's falling, but at some point between 2 and 2.5 it got to the top, and then it started going back down, right? So my guess is, and going back to this chart here, let's say this is 2 and let's say this is 2.5. Probably at 2 it was almost at the top. It got to the top maybe around there, and then by there it started going down, right? So from here to here, the average velocity is negative because it's going up, 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 stops, and then starts going down. By the time it gets 2.5, the down velocity is so much compared to the up velocity that we get this negative result. To 2.0 or to 2.1, it's still a little bit more negative than positive, but then as we get closer, it's more positive than negative, so we end up with this positive velocity altogether. So this instantaneous velocity, what we're approaching, if I had to guess, I'd say 0.4. It's not going to change by much. When you're 0.001 away, it's almost the right answer. It's not going to change by much. So for part D, I would go with 0.4 meters per second. I wouldn't argue with 0.5. I would argue with 0.2. Okay? Again, it's not going to go back the other way. All right, but it could continue a little further. But again, it's almost the right answer, 0.001 away. So kind of make that your judgment call. The questions in your homework tonight will have either this type of thing, asking about average velocity, where they give you just these intervals, time intervals. Make your chart like normal. How far did you go? How long did it take? Or they'll say starting at a time and lasting a certain amount of time. Make your chart. How far did you go? How long did it take? All right? But still keep in your bag of tricks the whole make a slope formula to do a t comma slope chart, and then the answers you get in the chart are the answers that are approaching there. So make a distinction in your mind about those two different ways of doing it. Be good at both of them so you have both techniques available to you. All right?